Thank you very much. I hope you all can hear me fine. If someone can confirm that.
Yes, we can hear you. Maybe you can share your slides.
Perfect. Sure will do.
So Binang, sorry, it will be good if you can restrict your discussion to 10 to 12 minutes so that we can allow enough time to all the other presenters. Thank you.
Sure. Okay. No problem. Okay, so I'll go ahead. As we all know, my name is Binang Gamit. I'm the project director at ESB. Today, I'm here to take you through the creation or the story of the creation of the world's first digital twin of a pump storage hydropower plant. So the project is called Extending the Life of Turlough Hill with a Structural Digital Twin. So Turlough Hill is the pump storage hydropower plant that is located in Dublin, Ireland. And digital twin is the technology that we utilized in order to optimize this power plant to extend its life. So let us begin. Throughout the presentation, I will first of all give you an introduction of the asset. Then I will take you through the whole journey of creating the digital twin, along with a few challenges that we faced throughout the way and the benefits of the complete product. So allow me to introduce you to the Free Electrons program. First of all, some of you might be aware of that. Free Electrons program basically is a global energy startup program. It is a collaboration platform for new and innovative technology and startups to collaborate with a few of the world's leading utility companies who will do pilot projects as part of the programs with these innovative companies and potentially commercially deploy those products within the industry as well. So if you would like to take the opportunity to be part of this program or would like to gain knowledge from this innovative collaboration, then join the program on 10th of November by scanning the barcode that is popping up on your screen, hopefully. It is a fairly highly innovative program, and it will be quite a source of knowledge for everyone. Okay, so taking you through the project itself. So let me introduce you to through a short video to the actual asset of Turlough Hill itself. So almost half a century ago, ESB took an astonishing decision of re-engineering the mighty mountain of Turlough Hill, which is situated in Dublin, Ireland. This was done in order to bring to life a cheaper, reliable, and renewable source of energy, which is generated within Ireland. And this creation was called the Turlough Hill Pumped Hydro Power Plant. As this is a pumped hydro storage power station, here's how it works. The power station is situated between the two lakes, separated by an altitude of approximately 300 meters. It has sort of two modes. One is the pumping mode and the other one is the turbine mode. It basically, in the pumping mode, pumps the water up in order to store it as potential energy and lets it run down in the turbine mode to generate electricity. Now, Turlough Hill has 4 such turbines, and it gives the total capacity, the generation capacity of 292 megawatts. So overall, Turlough Hill is quite a crucial power station that should be sustained for achieving a decarbonized and renewable energy future. Okay, so is this straightforward? Well, no, because the real backbone of the power plant is the penstock that runs the water up and down. And that penstock is half a kilometer long and is buried in a rocky mountain. So this creates huge amount of asset management challenges. Okay, so first of all, how do you access the whole penstock? It's a pitch black 4-meter in diameter pipe that has quite a challenging access towards itself. So if you want to optimize it, you have to access it by harnessing yourself and holding a torch and enter it into the pitch black pipe. That raises serious concerns regarding your safety. Also, how do you take call on how often do you have to inspect this pipe? And every time you have to inspect it, you have to go through an overhaul, which has overhaul costs, not to mention the loss of revenue that occurs during the overhaul as well. So in order to solve these challenges, we had to find ways to optimize this penstock. And the conventional ways that we all know are small-scale finite element analysis platforms or analytical fatigue calculations. Now, we all know that finite element analysis platforms are highly time-consuming. They are quite limited to the subject size. So you cannot design a large object with a huge amount of degrees of freedom and optimize it within a few seconds. It is not possible. Well, I should say it wasn't possible. You'll know now in a second why. So this kind of small-scale FEAs or finite element analysis could potentially create inaccuracies in the results. So we couldn't use them. Talking about analytical fatigue calculations, we all know that we require a huge amount of accurate data in order to perform these kind of calculations. Of course, with this kind of old asset, there is lack of data. Just to give you an example, the pressure extrapolation throughout the penstock simply didn't exist. So the data didn't exist. We only have sensors, a set of sensors at one particular location, which is near to the turbines on the penstock. The rest of 0.5 kilometer of the penstock doesn't have any sensors. And of course, if it is buried, it is not possible to have sensors at all the locations. So because of lack of such kind of data, analytical fatigue calculations could be inaccurate for us as well. So we basically needed something faster and much, much smarter. And that is when we were introduced to the Axlos workflow. Okay, so Axlos was a company who took part in the Free Electrons program. And thanks to the Free Electrons program, we were introduced to this highly innovative technology of digital twinning. So when we were introduced to the digital twinning technology through Axlos, we could realize the possibility of optimizing large scale structures within a few seconds, which is exactly what we required in order to accurately optimize the penstock of Turlock Hill. And therefore, ESB, along with Axlos, entered into the thriving world of digital twinning and created the world's first physics-based digital twin of a pumped storage hydro turbine. Now, digital twin, what is digital twin? It's simply a replica of the original asset based on a finite element analysis platform. But this replica has the exact same structural properties, metallurgic properties, not even that, but it also shows the exact same operational behaviors as the real asset. Basically, we can analyze the complete asset under one platform. And if I can say, we can twist it, turn it, or even break it before it breaks it into the real world. So let me introduce you to the creation itself. So as we know that the digital twin was a collaboration between ESB and Axlos. Now it's the world's first physics-based digital twin of a pumped storage hydropower plant. Just to introduce you to the mightiness of Turlock Hill, it has 2.3 million cubic meters of water only in the upper reservoir and 50 meters deep lower reservoir and a 0.5 kilometer long penstock. Okay, so it's a very, very huge asset. Now we had digitized all these 50-year-old engineering details and converted them into a live digital 3D replica. So this is the mountain overview of the penstock that is buried in the mountain. Okay.
Sorry, Binang, you will have to speed up.
Yeah, sure. So this is the complete model here. And I will take you through the model itself as we have the limited time. So the RBFEA technology, just to mention you the benefit, now we can mention or answer all what, when, and why questions that have been the nightmares of asset managers so far. So we can now know what is the exact current loading acting on the penstock, when it is going to fail, why will it fail, the exact location of the failure of the penstock. We can now mitigate the risk by applying the modifications within the digital twin model first and then optimizing it. And we can also know how much of life is remaining into a particular penstock or a particular asset. So the creation of digital twinning has happened in 4 stages: preparation of the CAD model, applying the boundary condition, applying the loads, and tuning the model. It sounds quite simple, but it is quite challenging. The first stage is preparing the CAD model. So this is where we digitize the whole 2D 50-year-old drawings into a complete 3D replica. But the challenge over here is to interpret the minute 2-dimensional details and converting them into 3-dimensional data and eventually creating this replica. The second stage is to apply the boundary conditions. So the loadings are, for example, here you see on the right-hand side photograph, green arrows are the internal loading in the penstock, but the envelopes or the pipe sections are, that are covered in the orange box are flexible to move because they are not covered by the rock or the mountain. Okay, so we have to give this kind of information to the software itself, and through the boundary condition, we do that. This is an example of us creating the behavior of rock and concrete within the software itself. So we use the spring elements and give them the exact same stiffness factors as the rock and the grout or the concrete and apply it to the model. So that's how we create the original asset within the digital replica. And this is the biggest challenge. Here we are applying the loads on the penstock. But as you see in the lower picture, the red dot shows the location of the sensor. The rest of the 0.5 kilometer penstock doesn't have any sensors. So what did we do? We took the data from the sensors, put it into one row of Excel, and then created a mathematical expression based on the fluid dynamics principles in order to extrapolate the pressure value for the rest of the penstock to the top, and then extrapolated it throughout the penstock. This is how we mitigated the gap. And of course, there were other challenges relevant to the standards that are applicable to this kind of application, the fatigue calculation method and tailoring the calculation formulas. We had to do that, obviously. And then after going through all of these challenges from the 50-year-old digital, 50-year-old non-digital drawings, we have the complete digital replica. And of course, there is validations as well. I'll just give one quick example that in one section of the penstock or the flexible envelopes, as I earlier said, we are deformating by purpose with exaggerated loads just to see where the deformation is going. So the direction and the magnitude. And if the deformation is not matching to the reality, we tweak the details so that it matches to the reality. Okay, and then this.
Binang, you'll have to, sorry, Binang, you'll have to summarize, please.
Sure. How many details, how many minutes do I have? 1, 2?
It's over.
It's over. Okay. So
yes,
just to. Okay.
Yeah.
Okay. Okay. So just to summarize, through the digital twinning, we basically reduce the operational cost because now we can, instead of having time-based asset management probably every 5 years, we are making it conditional based. So we don't have to assess or optimize the asset every 5 years. That saves a lot of cost. Also, we are extending the life of the asset itself. And we are making our asset management faster, safer, and remote. So that increases its efficiency as well. Thank you, everyone.